Hello everyone, this is Dr. Day with Physics 150. This week we're looking at something that is brand new to I think all of the students in the course, even those that had a strong high school physics background, and that is understanding these energy curves. So you can see more of this material on pages 262 to 264 in your textbook. And so I'm not going to cover anything that's really brand new to there, but I'm just going to kind of talk about that and try to explain what some of those terms are here. So what we're often showing you is what we call potential versus position curve. So what does that mean? So this is the potential energy, meaning when I look at the total energy of an object, I think of it as being the sum of its potential energy plus its kinetic energy, or just U plus K. And so generally speaking, the kinetic energy changes in a way such that all you need to know is the potential energy. So we go back and we look and we have our potential energy as a function of position. And that's how you know you have potential energy. It's positionally dependent. Wherever you are, it determines that energy. Now, some students have brought up the notion of a particle being trapped on a wire. What do I mean by that? Imagine I were to put an object right here, a ring, on a wire, and I were to let go of it from rest. What would it do? Well, if there's no friction, you would expect it to just sort of slide down, gaining speed as it fell. And then it would begin slowing down as it climbed up again, and then continue on up until the same height. Again, we're thinking, a wire sitting on a bead. And that's really a really great analogy, something for you to think about in this context. And that is, if I let go of something here, it's going to oscillate back and forth until this height, and then it goes back. So how do we think about that in terms of speed? Well, if I start here at rest, I have no kinetic energy. And as I fall down, I'm gaining kinetic energy. Well, the question is, how much kinetic energy? Well, hopefully you can see that with this being the lowest point of the potential energy, that would also be the highest kinetic energy. And so what we've got here is that this sum right here, this is the potential, and the remaining piece, this part right here, is the kinetic. So that potential plus kinetic is total energy. So when you're looking at this curve and you think about drawing your total energy levels, say I've drawn 3 here, what you need to think about is the distance from that potential curve to where the total energy is, that is your kinetic energy amount. So we can see here for energy levels E1, E2, and E3, they each have a different amount of kinetic energy, even though each of these 3 things is in the same potential energy curve. So what is this behavior going to look like? If I have E1, I have an object right here. What is it going to do? It's going to begin moving to the right. It's going to speed up as it comes down and then begin slowing down and come back up here to stop. And its kinetic energy is going to keep changing at each place depending on how much distance there is between. And at these endpoints, there's no kinetic energy or there's no speed, and this is what we think of as these turning points. And the object would travel this way, and then this way, and then this way, just back and forth. So if I tell you the total energy is this amount, I can't be over here, right? I don't have enough energy to be there, so I'm stuck here. Well, what if I tell you the total energy is E2? Well, now in that case, I have to tell you whether I'm on the left side or the right side, because each one of these is trapped to go back and forth. And this is what we refer to as a bound state. We often have bound states have a total energy of being negative, which seems to bother students, and I understand that. They say, how can the total energy be negative? Well, remember that the potential energy, we get to choose where our zero is. We get to choose where we think the bottom of something is. So imagine if I had a building, and that building was at some height of h. And I said, at the top, I'm going to take that to be 0 because I am throwing a ball up and down on the top of that roof. So why should I worry about everything below it? Well, if that ball, now gets thrown and it comes down, it's going to go to a y, which is negative, which is going to make my potential energy negative because now I'm below where I said my 0 was. But none of the physics is going to change. None of the calculations are going to change. A negative energy is simply a convention that we choose. So don't let it bother you. It really just means that we're in a bound state. So if I look at these 3 different circumstances here, E3 would traverse the entire well, but it's still bound. Why is it bound? Well, it's never going to leave this. It's always going to run out of velocity and turn around here, and run out of velocity here and turn around there. That is, the kinetic energy becomes zero. And so now let's think about, how do we describe the motion throughout? Well, if I look at E3, I would say that I have no speed, and then I begin accelerating as I move through. And that acceleration is going to terminate somewhere here around the bottom of that well when I now begin to slow down. Why am I slowing down? Well, my kinetic energy, which is this distance, is getting less. So I'm speeding up, slowing down, and then once I get to this side again, I'm speeding up and slowing down. So it really just depends kind of what's going on underneath. And if you want another sort of analogy for something like this, think about ocean waves. They're affected by whatever the terrain of the ocean floor is. You can, infer information by what the ocean bottom looks like based on what motion you see at the top of the water. It's kind of the same idea here. It just moves along. I'm speeding up, then I'm slowing down, and then I'm speeding up, and then I'm slowing down based on where I'm located. So the other topic that comes up in this material that we want to discuss is that you can actually, from this curve, get a force equation. And that is done by taking the derivative, and that is, we say that the force is equal to the negative derivative of the position variable of the potential energy. Now, how do you make sense of that? Well, let's look at our curve at this location here that I'm marking in purple. What is the derivative at that location as a function of position? And our choices are going to be either positive, negative, or zero. And so hopefully we can all say, like, oh, that's got a negative tangent line slope, so that derivative is negative. Okay, great. So the derivative is really telling you which way do you need to move to get to a larger value of the function. So at this location, if I go in the negative direction, I'm going to get to a larger value of my potential. Great. But we don't want the derivative. We want the negative derivative. So this says, which way do I move to get to a smaller value of my function? So the derivative is negative here, but I want to move in the opposite of that, or the positive direction. So the negative derivative is positive. So I want to move this way to get to a smaller value of u. What does that mean? Well, let's think about something on the other side here. And here, the derivative is going to be positive, right? But I want the negative derivative. So it says move in that direction to get to the smaller value of the function. And that is, we have this force which is dependent upon the slope of that curve, of this bowl. And that tells me how strong a force I'm going to experience to push me back to the center of this spot right here. And the same thing happens over here. There's going to be a force driving me back to that middle. You've already seen this. You didn't realize it probably, but you have already seen it. If you think about the potential energy for a gravitational well, that was going to be mgy. What is the negative derivative of that with respect to y? Well, that's going to be minus mg. So hence the force of gravity is minus mg towards the bottom. What else? Well, if you think about a spring, u is 1/2 kx squared. What is the negative derivative of that with respect to the position variable? Now we're going to get minus kx, and that is indeed the force of a spring. So I know everyone had to take calculus to be in this course. However, when we start talking about derivatives, students often get a bit nervous. We're really talking about the big picture. What does a derivative mean? It means find the slope of a line tangent to the curve. What's the negative derivative mean? Find the opposite direction of that. And so what we're trying to help you realize here is that you can tell how strong a force is based on that derivative there. So what does that mean? Well, let's imagine I had two potential energy curves. One was really steep and one was really shallow. Which one do you think would have a stronger force? And if you're not totally certain which one it is, please come see us in office hours. Thank you.